The next presentation will be delivered by Professor Stephen Collicott. He is a professor in Purdue University. His research interests are experimental fluid mechanics, low gravity fluid dynamics, optical diagnostics, and applied optics. So now he will present on manipulation of internal flows for spray creation.
Thank you. Thank you very much. It's great to be here. Thank you, Mahesh. Um, I was a little concerned this morning. You said we're here to talk about what we don't know, and that's going to take a lot more time. But I'll try to squeeze it down into, I had to stretch what I know to make 20 minutes, but to get. So this is a topic I've dabbled with for quite a number of years now, and there may be a little contradiction here with Jeff's talk in terms of the use of the word internal. I'm referring to up inside the orifice, and I got the impression from some of Jeff's slides, and he'll correct me if I'm wrong, that internal meant internal to the liquid core. But either way, there's fun stuff going on. There we go. Hydroentanglement is the production of non-woven one way of producing non-woven textiles, and they have spent a lot of time to create and stabilize hydraulic flip to prevent the spray, that is, to get a liquid stream. My group, we began focusing in this topic on the what we find to be intrinsically unsteady cavitation at the inlet of an orifice, because this sheds sub-diameter unsteady flow structures into the boundary layer flow. Now, I used to say it creates turbulent flow in the boundary layer, and somebody jumped all over me with the undergrad lesson of what 3 characteristics we call turbulence, so fine. Among friends, it's turbulent flow. This example here is a photograph of a chamfered single-sided slot inlet flow from the top down, 890 microns. And this is just a very low pressure, under 10 atmosphere flow, showing that indeed as the flow cannot follow the sharp corner here, it cavitates, and you're looking at this very, this is an instantaneous photograph of what is a very unsteady phenomena of this cavitation volume, the ripples in the structure here, the shedding of droplets, or bubbles rather, into the stream down beneath it. And it is interesting to me, 2 things about this image. One, I told the grad student this would be a waste of time to try to get this image, but it turned out so beautiful. And also, he's very wealthy now because he left engineering. So this is the young man, Mark Henry, here, who took that picture. Henry, Chandra, Sanchez, 3 really great young men I had the pleasure of working with. All 3 of them master's students on their projects here. Each explored the presence and structure of inlet cavitation in a slot flow. The slot flow was of interest because it gave us an unambiguous view. The slot had 1 tall block and 1 short block, as you saw, and that caused, let me review here, caused cavitation to happen on one surface. So when we viewed it this way, there was no ambiguity about what we were looking at. There was only one cavitation phenomena because this wall went up straight here. But of course, it would not really create a spray of interest to anybody, but we were looking early on at what the inlet cavitation would be like. In '98 then, Lee, Hyun Lee, who's now with Pratt & Whitney in East Hartford, Connecticut, concluded that for a tilted hole orifice, such as in a Cummins diesel injector, when the pressure is increased, the cavitation thickens and spray angle is increased. I'll show you some pictures from that. That was a true scale, true pressure visualization inside diesel hole, so 200 micron diameter, 2,000 atmosphere flow visualization inside the hole. Jamie Schultz did a little project looking at how particulates, solid particulates in the liquid alters inception and hydraulic flip of the cavitation. Had some really expected and unexpected impact there. We never got around to publishing that. David Ong, and I, once we realized how unsteady this cavitation is and how it is always shedding sub-diameter length scale unsteady flow structures into the boundary layers in the flows and affecting sprays, we went to say, well, given this natural unsteadiness, how can we manipulate it? How can we put it to work for ourselves? Can we make it more unsteady and cause different droplet productions and that sort? So this is very exploratory work, and I'll show you with some figures later how a simple small step in the orifice wall really had a big impact on the cavitation, hydraulic flip, and droplet production. And then David Seng, actually David Ong is now a successful consultant in mining engineering in Australia. Seng's in Taiwan National University as a researcher. So we demonstrated, given that a small step would work, we wanted to have a way to turn that on and off, modulate it. And so we went to a fluidic control of this step-like phenomena, and that's what Seng did. In the diesels, this was Lee's work, so we had a 14-degree tilt working with Cummins. Back then, Caterpillar was running 17-degree. This was before laser drilling. These were EDM holes they were interested in. We wanted optically accessible holes. So they were basically drilled in acrylic. Laser drilling failed. A lot of laser drilling companies back then told us they could do it, and nobody delivered. Water jet for the untilted holes was real nice, but for tilted holes, we were back to just plain drilling. Lots of coolant and drilling. So the orifice holder here, we were going up to 210 megapascals. Cummins helped us with the structural analysis. The orifice sits right down in here. This is the feed, and this is the darker gray is a chamber here that provides two holes for optical access. It's just run off a 30-to-1 hydraulic intensifier, so running 1,000 psi nitrogen for 7 megapascals and producing 210 megapascal oil. For the spray, we had about a quarter liter of a liquid, but that would last for 20 seconds, and 20 seconds is plenty long when the oil is only, the transit time of the oil through the orifice is 1 to 2 microseconds, so 20 seconds is forever. As far as the internal flow is concerned, this made it real cheap. We could do this, run this very inexpensively. There's an image of the hole with no flow. Okay, so the flow is going to be from top to bottom, and here's some examples of all kinds of things going on inside the orifice. So anything that's black here that was not black here is something going on in the flow that scatters light out of the lens of the camera, okay, which would be a liquid vapor boundary. Okay, so this is only at 87 megapascal. This was some pretty pictures here. You're seeing there's something going on along the right-hand side there. A type of cavitation going on there. You're seeing some surface roughness effects show up here and there. These are different, left two are slightly larger orifices. These two are 206 micron. And just going down a little bit in length scale, you're seeing different phenomena. And we saw basically three types of cavitation going on. So again, true pressure, true scale. Experiments, I think that's the only way to go, as none of us are smart enough to scale these phenomena. There's so much going on with surface roughness, gas constant. Actually, and when you start to look at a diesel, when we're talking about simulants, well, what really is vaporizing in here? It's not a pure liquid, right? It's a blend. So what component is vaporizing where? And there's just so much going on. I don't see how we can try to scale this up, and it's a non-equilibrium process. The bubbles are growing, the bubbles are collapsing on the same time scale as it takes to flow through the orifice. So that's my big push, is we got to go true scale, true pressure, especially if you want to connect up to sprays out the outside of this. Okay, so that was the high pressure work. But what I want to talk more about now in terms of controlling. And there's a lot more that could be done with that high pressure work. If we talk about a plain orifice here, then to turn the flow to enter the orifice, as you note, on the inside of those curved streamlines has to be lower pressure. When that drops to vapor pressure, then you get the cavitation shown in the little white region here, okay? So there's the vena contracta in there. Cavitation ends at some streamwise position, And interestingly enough, the flow downstream of that always seems to be, from best people can measure or from CFD, it's not like a wake, it's really more of a reattachment flow along the wall. And we'll make use of that here. So this unsteadiness from the upstream edge is steady, okay, where the cavitation begins, usually is pretty fixed. But the downstream edge oscillates back and forth. And so this is, and then I mentioned it's like a reattachment flow. It's not like a wake. And so we thought this is like the downstream facing step flow in single phase fluids, steady separation, unsteady reattachment. Talked to some folks working in that field in aerodynamics and said, what would you do to make that reattachment flow less steady? What would you do to make it more chaotic? And the answer was you'd put a small upstream facing step at about the mean position of the reattachment line. So on the left here is a sketch showing the cavitation region and a streamline coming around it and reattaching to the wall right around here. Well, if we take that over and put an upstream facing step there, so the exit diameter is the same for each hole, and we've enlarged the entrance a little bit. And our thinking here was that this little upstream facing step creates a higher pressure region in the flow, and that should collapse cavitation, and maybe it'll have an effect. We were exploring, okay? And we got some fun stuff going on here. This blue hump here, droplet size in microns across the bottom here. The blue hump, that was just the plain orifice. All right, and then we had two steps here, a small step and a large step. And look at what the large step has done. It's really dropped down that large diameter peak and created this very large sub-diameter peak there. So something's going on. And other things that would go on with this is the imaging work would show that indeed this step is limiting cavitation to the region above it. And an unexpected thing that came out of this was also that, this is what I was starting to talk to, that the upstream facing step makes a little high pressure region, collapses cavitation, prevent the downstream growth. The shorter cavitation region seems to oscillate faster, creates higher frequency structures shed into the boundary layers, which then affect what's going on out here. All right, so the other thing it did, I don't have the slide here, I think I have it later on. The other thing it did was it altered hydraulic flip, or when does the cavitation extend all the way to the exit and out the exit plane. It required a much higher pressure, driving pressure difference to create a hydraulic flip. Whether that's important or not for people, who knows. So this was Ong's work I was talking about, and it's further proof that cavitation affects droplet size, although this was a very low speed liquid jet breaking up in the droplets. This was not a spray, as you would typically call it. But it does produce droplets significantly smaller than the orifice diameter. Well, we wanted to know how could this be extended such that this control effect could be modulated. Could we get big control, small control? Could we turn it on and off? So that's where the work with David Seng came in, where we tried to demonstrate a fluidic method to create the effects of the step seen by Ong. Okay, so again, going on the theory that, and there's some CFD involved which backs me up on this, but the upstream facing step creates just a little region of elevated pressure. You don't have to get much above vapor pressure to collapse the cavitation. So we thought, well, how can liquid injection do that? And the answer is to have the liquid come in and get turned downstream. That process of turning the streamline downstream needs higher pressure above it than below. And so maybe if we inject liquid upwards like this, that for it to be turned and flow down out the exit will create a similar pressure field as the step. And so we built a transparent system here, kind of a cylindrical plenum with a conical injection slot. It's just the void between two pieces here. These are both in acrylic, so we can see, and again, some low pressure work. and hooked up with usual stuff. That's what they look like there, sitting on the table. That's the inner plug. That's the outer or the main housing, and this goes in the bottom here. And you see this cone, and the gap between those two cones is the conical injection slot. And so the main flow comes into this fitting. The secondary flow comes into this fitting. They're the same liquid, these two flows. We just, there's a T up above. You take some off, meter it however you want to create different ratios. So there's nothing chemical going on here, and it's not an effervescent. It's two liquids. And we started out to replicate the step geometry of Ong that worked so well, and went at this. And indeed, with nothing going on, zero secondary flow, you get that peak there. Then you start to grow these smaller peaks with the injection there, and again getting down to this with increasing injection, in this case 4% secondary flow, starting to grow this peak here down here of the small droplets. Now, and these pictures don't show the cavitation very well. That was looking through that conical injection slot, really mangled the optics a bit. And as you saw in those droplet measurements, it was working like the step, but nowhere near as well. Okay, we produced a lot fewer small droplets, and it's really a lot of open questions about how far you can go with this or not. And we've been trying to pursue this more, and I'll show you what coming up here where we're headed next. We did do some internal CFD based on my colleague Steve Heister and his pseudo-density model. This is now getting into some vintage work here. It's not currently a model in use, but this is some older work here. And in there, this being the center line of the jet, and this being the injection slot there, and Z star of 0 is the inlet. So we have streamlines here on the right showing a little cavitation region up here. We have pressure contours here showing the low pressure up here by the inlet corresponding to that region there. And indeed the flow coming in here has caused this elevated pressure upstream of it. So we confirmed that we're getting the pressure behavior going on. Now we took this also to, we ran axisymmetric unsteady, and we're trying to sort out, well, what really is going on in these internal flows that's creating the effects we're trying to see. And that ended up largely inconclusive, because we had a second style of injection slot we also ran, and the internal structures in those two flows, even though they both altered the droplet production, there were vastly different internal flows going on in terms of the oscillation and whether the cavitation extends past the injection slot or oscillates up and down, and many other things going on. So that really turned out to be inconclusive initially. This was the discharge coefficient measurement. I wanted to point out that the blue triangle here, 0% secondary flow, so that's just a plain orifice. And you have the traditional drop here with hydraulic flip, okay, right here around 380 kilopascals. And as we turn on, this pink square is the 1% secondary flow. So as we start to put in some of this secondary flow, discharge coefficient is altered. We know from the imaging that it's controlling hydraulic flip. It's forcing the cavitation to stay within the orifice rather than extending past, or extending all the way down and out the bottom to create hydraulic flip. And here, even with 2%, we get a huge change, and up to 3, 4, and higher percent, there doesn't seem to be any evidence of hydraulic flip, and our facility topped out at that number there. So these little changes inside the orifice are causing some big changes in behavior. So the fluidic control conclusions, this orifice I talked about works exactly like the step at some secondary flows. It confines cavitation to the regions upstream of the step, upstream of the slot. It controls hydraulic flip. The other one worked differently, but neither orifice is as effective as the step. And so really further research is needed to try to understand better what really are we manipulating in the flow. I keep talking about cavitation. That's the most visible thing. It's easiest to point your finger at it and say it's long, it's short, it's unsteady. But really, there's a lot going on here. And this is the flow. This is creating the flow that feeds wave growth and primary atomization, and maybe even, pardon me, wave growth and primary atomization outside the nozzle. So what's going on inside seems to be affecting what's going on outside. And Enrique Portillo, working with Professor Greg Blaisdell and myself in my lab, did some neat work on wave growth rates on a liquid jet. Recently, Enrique is now doing combustion stability work for Siemens turbine engines in Orlando, Florida. And this flow that Enrique did, looking at wave growth rates, really gives us an excellent reference case now to use to document really well the effects of internal flow structures on wave growth, jet breakup, and atomization. All right, so we are setting up now. I've got a new student, Guillermo Jaramillo from Colombia, a very energetic young man in his first semester, just finished his first semester with us. So we can create a variety of boundary layer thicknesses at the exoplane of the orifice to examine boundary layer effects on the wave growth. This is Enrique's PhD work. It'll be out in the next month or two in Physics of Fluids. We just reviewed the proofs. And my approach is why wait for wave growth models? So we're moving on to create large amplitude disturbances to the flow and investigating the impacts of these large amplitude disturbances. Wave growth models look at small amplitude disturbances, growing waves, and that's great. That's important work. In addition to that, I just like to explore. Let's see what these large perturbations can bring us. So here's an example of the nicely behaved jet from Portillo. This is the orifice plane right here. Okay, to the left of it, it's merely a reflection off the end of the nozzle. And so flow left to right. And here's one example. This happens to be a thin boundary layer coming out. And you can see the classical wave growth out here on the edges. And you can see nicely what it looks like here. Hoyt and Taylor have a couple pictures for decades. Everybody's been pointing at Hoyt and Taylor. Portillo here has many of these under many conditions. He did some very, very nice work under Greg Blaisdell's guidance on the big picture. I just helped them get the pictures create the flow and get the pictures in my lab. Another example here, obviously the waves starting closer to the orifice. Here's the orifice here and growing differently, waviness in them. Another example here, nice laminar jet coming out, growing into waves that never really have the classical, growth. They're more wave packets around the perimeter. Here's one here. There's one up there. There's a void here. There's another one down here. So we've got a real nice facility here. This is with a much thicker boundary layer. And there's one where a lot of fun stuff is going on, again with the thick boundary layer. And some laminar regions here, other regions, it's coming out of the nozzle turbulent right here, okay? And obviously, if you were looking at a cone angle, you'd see that there is an angle here and there's almost none on the other ones. Ligaments up here already forming and throwing off from the jet. How can we make this happen faster? How can we make this happen better? How can we control spray properties through working not out here, but over here inside the nozzle? That's the type of fun work I've been exploring. So we've we don't dare touch. Enrique had 3 beautiful nozzles he designed and built, and those we've left alone, but we're making a 4th one that right now that matches the middle of the 3 of his that we can now insert various activation devices upstream of the straight section of the nozzle here and start to create fluidic or mechanical excitations of the flow and say, you know, how much turbulence, how much small, you know, sub-diameter length scale high frequency structures can we send out the orifice to try to affect what's going on in the spray here. So that, oh yes, and a lot of quantitative work out of Enrique's images too. He did some really good work on image processing to get out the quantitative information out of these. So these are an example. This is from the paper that'll be out here in a couple months. And so this is really, the first paper is about wavelengths that are created. The second one is growth rates. And the third paper he's hoping to get has to do with the circumferential structure on these waves. And again, none of this would have been possible without my colleague Greg Blaisdell lending his brilliance to the project. So wavelength versus Reynolds number, the Reynolds number based on momentum thickness of the boundary layer on the nozzle wall. So, oops, there's the pointer. L over D1 is the thin boundary layer case right down here. L over D, that's length and diameter of the nozzle, of the straight section of the nozzle. That affects boundary layer case. L over D10, he never really got, you know, you're not really measuring any coherent wave on that. So these are results, and then these are constants for several proposed fits people have for these wavelengths. So this is going to be our baseline jet now that we can go and manipulate the internal flow in the orifice and explore, okay? I don't have a theory of what's going to work best or not in this. We don't have, the way this one's put together internally, we don't think we have much in the way of cavitation, but we want to play around with the boundary layers and the turbulence in it like Hirayasu. So to conclude, internal flows definitely affect spray formation. Internal flows being flows inside the orifice, I would say even upstream of the orifice. If you look at some of the SAE papers, you'll see structures upstream of the orifice in the fuel sac. Therefore, internal flows affect the wave growth and the breakup modeling. And so maybe, you know, a decade ago I didn't sell this well. I'm not saying don't do modeling. I'm not saying don't do wave growth. I'm saying besides that, this exploration is useful because what's coming out of these nozzles is the input to any modeling you do outside of the nozzle. So we know we can tailor the flow inside to produce many subdiameter droplets from a simple orifice under some cases, and we want to keep expanding that. And there just are a lot of options out there for creative manipulation of the jets or sprays. And I had a controls colleague who kept trying to talk to me about putting active control on this, and I just kept telling him active controls for when you're not smart enough to make a good passive system, right? So someday, yes, maybe, you know, this can easily couple into acoustic work or other outside the orifice or other things upstream, but for now this is where I've gotten to. So thank you.
Thank you, Professor Collicott. We have time for a couple of questions. Yeah.
I guess I did mean internal flows, internal to the nozzle, because, you know, the characteristics we see are generally the same diameter, same L over D, but some differences in hydrodynamic grinding giving us some different rounding of the edges. I'm wondering, did you ever measure this any dynamic characteristics in terms of frequencies of the oscillations?
Okay, yes, the dynamic oscillations we did, but never for the diesel. We did it on the lower pressure flows. And
Injector, how they would scale or what kind of frequencies you would expect?
not over that big of a difference, I wouldn't conjecture. On the lower speed flows, there was a primary frequency that really was very closely related to, let's see, take the envisaged Bernoulli velocity and divide by the length of the cavitation region, and it was always very close to that. Now in the diesels, those pictures I showed you, there is no unique cavitation length like in the low speed work. We ran across 3 types. There was inlet cavitation, surface roughness cavitation, and then the cores of counter-rotating, a pair of counter-rotating vortices created by the tilt going down. And so, no, I would love to look at that more and see what else we can pull out. For the electron discharge machine drilled holes, my main conclusion was my acrylic holes were too smooth. That is, it is in those holes it was a boundary layer roughness interaction. I think had a lot to do with the spray. I'd love to see I don't know what the new laser drilled holes are like for roughness. But
I think if you look at the stuff that Argon's done, they've done a good job of profiling in the nozzles. You've got some pretty detailed information of what the internal nozzle.
Oh, that's nice. Yeah, and that tilted hole or with a normal hole with cross flow, either way it's a 3-dimensional entrance flow. You do get that pair of streamwise vortices, and so a tilted hole or a straight hole with cross flow is in some sense a swirl injector too. That was and so the whole issue of is there enough swirl there to put to work for yourself? I don't know. Did I probe the injector for turbulence? No, certainly on the diesels we weren't going to get inside to see what was there with a 200 micron diameter in terms of measuring something. With the slot flows, that was a very large plenum, so we were assuming laminar in there. With everything though, it starts to get to the point of what's happening in the nozzle depends on almost everything upstream. With Enrique Portillo's wave growth measurements there, those nice photographs at the end, I annoyed him tremendously by making him move the supply line, move the supply hose every which way he could and see that he got the same results. Because I've just become so suspicious of every upstream corner shedding turbulence down into the flow for bubbles. So we didn't measure directly. The Reynolds number I know off the top of my head would be for Enrique's work based on momentum thickness of the boundary layer. So that was 100 to about 700 or 800.
Thank you, Professor Collicott.